Imagine that you are working on a distributed system. So your application runs on multiple machines. You probably have multiple microservices, multiple components. There is some database, file storage, service bus, queue, whatever else. You can imagine a lot of these things running in parallel. So then a user comes in, hits some load balancer, then the request is routed to some web server, and the workflow starts. So probably something hits database, file storage, et cetera, multiple components are in play. And then, because all of this is distributed, something runs in London, here in UK, some other machine runs in Seattle, some other machine in Tokyo, Japan. So generally, those things are all around the globe. So things, they do fail. This is typical in distributed systems. So now your user gets an error message telling that, hey, something went wrong, et cetera. And user comes to your support saying, hey, please fix this. This is some idea of the workflow, et cetera. Go and figure out what happened. So now comes the question. How do we structure our logs, or how do we log information in the distributed system so we can figure out what exactly happened? What happened not necessarily, not only like in which components, but also in which order. So how the things were executed, especially that we are talking distributed systems here. There are very long network calls. There are things running on the west and east side of the globe. There are things running in parallel and running serially at the same time. So during this talk, we'll try to figure out how to log information in the system so that later we can extract the order of this information. So we can recapture the order of how the operations, how all the steps were executed one after another. So that's the point. And during this talk, we'll figure out how to add some ordering to the chaotic world of distributed services. Before we move on, a few words about me. I used to be a .NET developer. Now I'm a machine learning big data guy at Amazon Seattle. I'm also a blogger, public speaker. Feel free to drop me a line on Twitter, email, whatever works for you. At the end of this talk, there was a QR code pointing you to the slide deck, so you can download this deck and walk it through on your own time. Also, last year, I released this book called .NET Internals Cookbook, which explains a lot of things which are running under the hood in .NET, how memory management is structured, multi-threading, shim, how interops with C++ work, etc. So if you are interested in these things, feel free to take a look. It's meant to be succinct, so it's like a series of questions and answers with links pointing to various sources. So it's just like the beginning of the journey. OK, let's move on. So agenda for this talk. Like, we started with stating the problem, OK? There is some logging. We would like to recapture the order of steps in our system. So the most obvious solution which probably comes to our mind is, why not just log the timestamp when we are doing any logging? So logger.log, provide a timestamp, provide enough details what's going on. And the thing is, timestamp and walk log in general doesn't work in distributed systems. And it's proven that it won't work. So in the first part of this talk, I'll try to show you what problems we may face when we are working with time in distributed systems. And by time, I mean here mostly wall clock, like the time saying it's 2 p.m. In London, for instance. So then we'll figure out, after seeing that clocks, they do not work for us, we'll figure out what we can use instead of using wall clocks. So we'll see how to avoid clocks in computer science, and then we'll see some real implementation showing you how to make these things simple and yet working correctly. Ultimately, we'll just go beyond the time and we'll focus on some broader computer science problems, like how to solve consensus or how to introduce like total ordering in our system, which is not the main point of our problem we are solving, but still something we can generalize later. So what is time? Like, the obvious solution for ordering the logs is we extract all the logs from all the machines and we sort them by the timestamp, yeah? The only problem with time is, apart from like some physical definition that is like transitions of cesium, this many transitions in each second, is that there is no global time. Every single machine, every single clock, every single watch on your wrist is basically showing different time. And while for us human, it's not a problem when it differs by a second or even by a minute, for computers, it gets really serious because all the operations we are running in our systems, they are pretty fast. Operation can execute in like nanoseconds. So if our clocks, they differ by a second, it's way too long for the operating system and for the machines to figure out what is going on. And also, because we are using clocks and we need super high precision, clocks tend to increase their error rate when we increase the precision. So when we would like to have like nanosecond precision for our watches, like the error rate, so the time when clocks go out of sync is increasing significantly. I mean, it's much faster. It can be after a few seconds. Obviously, clocks can differ not only because of their like problematic construction, but also because the operating system or the machine you are working on is actually moving. This is like a law of relativity by Einstein telling us that, hey, the higher we are above the Earth and the faster we move, like the time changes. So basically, these are things which we need to take into account when we are implementing distributed systems or things like which are working in the space or working on a plane. So using a time is not necessarily super simple in the scenario we would like to consider. But also, when it comes to the time, there is yet another issue, which is called a time zone. And whenever someone mentions a time zone, we tend to think about whole number of hours counted from UTC. So we say the time zone is UTC plus 2, for instance, or UTC minus 6. Unfortunately, that's not the answer, because we do have a thing called daylight saving time. And in daylight saving time, we basically change our clocks. We move them like forward by 1 hour or move them back by 1 hour. This is what we typically do. And we may think that DST, daylight saving time, is simple because, hey, it happens every single year. And we generally more or less know when it's happening. The problem with DST is around the globe, it happens on different time. Like most of the European countries, they change their time like end of March, and they move forward 1 hour starting at 2 a.m., so they move to 3 a.m. and they are good, but it's not always the case. For instance, United States, they change the time for DST like a week earlier or a week later than the Europe does. Also, some countries, they introduce DST at midnight or 5 minutes after the midnight. Not to mention that the countries, they change their regulations. For instance, European Union now passed a law that each country can basically decide, hey, are you staying on DST or not? And if you are not staying on DST, you can choose whether it's winter time or summertime. So these things, they do change. They are not carved in stone, and unfortunately, it's very hard to reason about the time, like when we are considering things which are happening in the future or in the past. Because if we imagine a very simple ticketing system, for instance. You would like to book a flight which will depart at 8 a.m. half a year from now. How do you show it in your calendar for the user? Because if you show it at 8 a.m., then half a year from now, probably the user will be in different time zone, will be in DST or summertime or whatever else. So then it may be showing at 9 a.m. instead of 8 a.m., and this is a pretty serious bug. However, if you show it currently at 7 a.m. or 9 a.m., depending on which side of DST we are going on, then the user may come in and tell you, hey, this thing is showing me incorrect time because I booked a flight at 8 a.m., departing at 8 a.m. So generally, these things are not simple when we consider them globally, across the globe. And also, time zone, or like the whole number of hours when we typically think about time zone, this is not obviously the same around the globe. There are countries even now which differ by like 30 minutes or 45 minutes. But if you take a look at some historical data, it's getting even more interesting. I'm from Poland. So if we take a look at Europe-Warsaw time and get some very old date, like end of 1899, and we check, hey, what was the local time at 7:20? If we start converting this to Europe-Warsaw time, getting this very old date, we actually end up with something which is basically 7:44. Why is that? Because at that time, Warsaw was using time zone plus 1 hour and 24 minutes. And these things, they unfortunately changed a lot. So then we were introducing wintertime and summertime between 1957 and 1964. Then we dropped summertime. Then we restored summertime. Now European Union passed this law, so we may drop the summertime again. These things change. Not to mention that right now we moved to summertime like end of March, but we also did it like in June 30 or 40 years ago. So these things are getting very, very tricky when we start considering just a very simple term like time. Also, when we consider what is the time zone of various countries around the globe. It's not always the case that the bigger country, the more time zones, because for instance, US has multiple time zones. But if we take a look at China, China runs only in one time zone. It's also getting even different, for instance, in Russia. There are multiple time zones, but once you step through the door to your train station, you change the time zone because all trains, they run using one time zone only across the whole Russia. So these things are pretty tricky, and they change significantly. So relying on time zones around the globe may be super hard for you. The things with DST, just to wrap up this topic, they are even interesting because, for instance, take United States. United States, they do have summertime and wintertime, unless you are in Arizona, which is like here southwest of US. Arizona doesn't follow summertime, unless you are a Navajo tribe in Arizona. They do follow summertime. So it's not only sufficient to tell you, hey, where you live. You also need to say, hey, who you are. So generally, time zone is a region of the globe which is observing the same time. So it's super hard for computers to follow correctly. Also, there are two terms, UTC and GMT. We tend to use them like interchangeably. UTC and GMT, that's the same. Unfortunately, they are completely different. UTC is based on atomic clock, and it's supposed to approximate the GMT time. This approximation is allowed to differ by up to 0.9 of a second, so 900 milliseconds. That's why UTC needs to introduce a thing called leap second. So it's like 1 second, which is sometimes added, can be also removed, but this never happened, but it's allowed by the standard, to adjust the UTC to the GMT. GMT is tied to the rotation of the Earth, the way the Earth rotates and goes around the sun. So that's why, because you probably know that like 1 year is not exactly 365 days. It's also like the 6 hours and something else. So these things go out of sync pretty often. And when it comes to leap second, assuming you still would like to rely on a time, the leap second, which seems seemingly easy, so like it's 1 second introduced to your clock, can, for instance, take down half of the world. And this actually happened something like 8 years ago. There was a bug in Linux kernel, so the task scheduler was going completely crazy. And you had a very big CPU spikes for like few minutes just because this 1 second was introduced. And MySQL was going completely down. You had to reboot your machine or reboot the service to get it working. So generally, this already happened, and we may safely assume it will happen again. However, this time we should be a little more prepared because instead of introducing this 1 second, what we do now is called time smearing. Time smearing is we take this 1 second and we basically make all the seconds of a minute slightly longer. So it's not that we have 61 seconds in a minute when we introduce leap second. We have 60 seconds, but each second is lasting slightly longer than 1,000 milliseconds. But things get even like harder, assuming that we would like to synchronize these clocks somehow. So I told you that time zone changes, and for instance, each country can decide, hey, we are dropping time zone, we are dropping DST, we are moving to different time zone. So how do our computers know what is going on? And this thing is called TZ, or time zone database. It's distributed by an organization called IANA, Internet Assigned Numbers Authority, which is publishing multiple times a year a database, TZ Info, which tells you exactly, hey, this place has this time zone, so this is the DST, etc., etc. Obviously, there is some nice RFC, and there is some nice updating this package through your probably apt-get or whatever else. Raise your hand if you were aware of this package. OK, I can see a few hands. That's great. For all of you who were not aware that this package exists, well, things are getting even more interesting because obviously it couldn't be that there is one package. There is a thing called CLDR, which is in Microsoft world and in Apple world, which is also emitted periodically and also tells you not only the time zone, but also the locales. So for instance, if you have seen NUS or NGB languages, this is basically stored in this database as well. The problem with CLDR and TZ Info is that they are out of sync. They are not synchronized. They use completely different names. So generally, if you do have Windows machine and Linux machine, like, good luck with synchronizing the clocks. However, the thing is, OK, there is a TZ database, which is distributed. And we do have time, which we can store in local time or UTC time. And now when we ask a question, hey, should I store my time in local or UTC? You go to Stack Overflow. Stack Overflow tells you, go with UTC. There will be no problem ever. OK, so let's see how it works. And UTC is not a silver bullet because things, they do change. European Union passed this law, so let's see what may happen in your applications like soon, in 2 years. So we would like to organize some event on September in 22 at 9 a.m. in Amsterdam. Currently, the time zone or the time offset from UTC for Amsterdam on September 4th, 2022 is expected to be +2 hours. So what we can do, we can take the time, store it as UTC, and Stack Overflow said, hey, it's going to work, so let's see. So we take the time. It's 9 a.m. We subtract 2 hours to get the UTC time, so we have 7 a.m. That's what we store in our database forever. But then Amsterdam or the Netherlands, they decide, hey, we are not going to use DST anymore. We'll just stick to winter time. So after some time, which we don't know yet when they are going to pass regulations and make the decision whether it's winter time or summertime or whatever else, like they do make this difference. And then they are expected to be +1 on that September 4th, 2022. So on September 4th, we go to database, we get the UTC time, which is 7 a.m. We check the time zone, hey, this is +1. We move 1 hour forward, and we end up with 8 a.m. So this thing is now broken. If you ever store your timestamps for events in database and never, ever update them, raise your hand. Yeah, so you may go then check out what's going to happen in European Union in 2 years. OK, so that's not the solution, obviously. With UTC, can we do better? Obviously, we could do better. We can store as UTC, but we need to update the time. So there is this TZ info database, or CLDR, which is distributed periodically. Whenever we get a new version of TZ info, we get the UTC time. We calculate local time using old TZ version. Then we calculate UTC time using new TZ version, and we update the value in database. Pros, well, this solution works. Unfortunately, this is pretty hard because we need to store not only the current TZ info, but also the old one. And not only we need to store the UTC time, but also the version of TZ info which we used to store the time. So these things are getting slightly harder. The other solution, which we could use, is basically store this as local time, but not necessarily as like date time or timestamp or whatever type you are using in your language, but as something strictly saying, hey, event is at 9 a.m., like a string or whatever else you can imagine. You do keep this, and then you don't care whether TZ info was updated in the meantime or not. You just grab this thing, and you recalculate this accordingly whenever user asks you for the answer, hey, when this thing is going to happen. And this is actually the source of truth for the event, because the organizer of the event came to your system and said, hey, I'd like it to be at 9 a.m., not at UTC or UTC +2 or whatever TZ info version. That's the source of the truth. So I'm not saying this solution is better or worse than the previous ones. All I'm saying is there are multiple approaches, and using UTC is not necessarily the best idea or is not necessarily going to solve all your problems. And also, just to wrap up the topic of time, if you can read some sentences on this slide, for instance, that minute has 60 seconds, etc. And the thing about these sentences is all of them are wrong. None of this slide is actually true. So let's go through some of the gotchas with time. So a month begins and ends in the same year. Unfortunately, this only started to happen depending on the place you were living in different centuries. For instance, France started observing New Year on January 1st in 1564. But Poland or Russia, they made this decision in different time. So generally, your month can start and end in different years if you are working with historical data. February has 28 days. We obviously know this is not true, like once every 4 years, unless once every 100 years, but once every 400 years. We get February 29th. And also Sweden, when they were adopting Gregorian calendar, they thought, hey, like all the countries, they basically skipped 11 days, because that's how many days they had to adjust to the Gregorian time. But Sweden was clever. Let's not skip 11 days. Let's just introduce this. They are introducing February 29th every 1 blah, blah, blah days. We will just skip that. Yeah, that was a good idea. Only the war came in, and they forgot to do this thing, so they went out of sync. And 1 year, they decided, hey, let's introduce February 30, and let's get rid of this problem once and for all. Not to mention that there are other calendars like Symmetry 454, which has 35 days in February. Hopefully, we are not working with these things. A minute lasts 60 seconds, or something like this, but definitely not hours or days. Unless you are working on a virtual machine supervised by KVM on CentOS, and you have version which had this bug. So when you were putting your machine to sleep and then resuming it, this clock went out of sync. So your minute could effectively last hours. So generally, those are issues we do have when we are working with time. So assuming that you would like to use the clocks in computer science, well, you need to face at least some of them. But let's say that we are working this year, not something like 16th century and not in Sweden. Let's say that we want to use this clock like only in few data centers, but in one time zone. How can we do that? So we need to synchronize clocks. And while it may sound to you that, hey, there should be super brilliant, clever algorithm for doing that, there is one, and it's basically, hey, what's the time? Oh, it's this time. And you ask this question multiple times, one after the other, and then you try approximating what the real time is. The problem is you ask this question over the network, so you may imagine there is some latency. Unfortunately, this latency is not stable. You may get different lags, different delays when you ask this question, and you don't know how long the processing time on your CPU takes. So generally, you just ask this question, you get some answer, and you cannot assume anything about this answer. But if you ask this question multiple times, you may feel like, yeah, we're pretty sure what the time is. We should be in sync right now. Obviously, this in sync means here something like down to or up to microseconds best, probably more like that up to milliseconds. But generally, we should be in sync. And there is a protocol for that. It's called NTP, Network Time Protocol. It's based on the idea of stratas. So we just group the machines in the layers. Each layer we call stratum. So the machines which have access to the atomic clock, they are in so-called stratum 0. They should have like perfect clock, obviously perfect to some physical relativity, etc. And then they just broadcast this time to the machines connected to them directly, to the stratum 1. And then this follows to different stratas. And obviously there is a slightly more sophisticated algorithm for NTP, which is still based on the same idea. We just ask the question, hey, what's the time? But we try to approximate the latency, the network delay, the processing time, all these things. But this is how we basically synchronize time. So there are also other approaches like different algorithms which try to be slightly more clever. One very worth mentioning is called TrueTime, which is algorithm used by Google in their Spanner database, which basically guarantees you that you are synchronized down to 7 milliseconds. So you can actually order events based on this time, but the idea behind this database is because I don't know whether I am 7 milliseconds ahead or behind, I just need to wait these 7 milliseconds and figure out whether new message comes in. If it does not, then I can assume my timestamp was correct with these things, etc., etc. But anyway, all these algorithms are based on this flawed approach of like clocks being not perfect. So ordering events in distributed systems based on timestamps is not necessarily going to work. So let's see what we can use instead, how to avoid using clocks in computer science to order the logs. So once again, user comes to our system. We would like to log some information from multiple machines, from multiple nodes. So then we can later capture all these logs, log entries and order them so we know in which order they were actually happening. So what we would like to do is we would like to have like some working notion so that when we have two events, A and B, we can say that A happened before B. And we would like to have this guarantee that A happened before B, not some approximation. We would like to do it over multiple machines over internet. So one machine is London, the other one is in Seattle and in Tokyo. We want it to be fast, generally fast. So we don't want to wait like seconds or whatever else. We would like for it to work as fast as possible. And we are also interested in events of only one workflow, meaning that user A comes to our system, and we want to figure out what the events for user A were only. So if user B comes to our system at approximately the same time, we don't want to compare these events whether user B was earlier or later than user A. That's beyond the scope. What we would like to do is only order events for user A. So what we are going to implement is a thing called Lamport timestamp or Lamport happened before relation. So we say that event A influenced event B, and we denote this with this arrow notation. And what we do is we will be able to order events as long as one influenced the other. So this notation, or actually this theory, allows us how to calculate these things. And the idea is super simple. If we are running on one machine, then we are executing like our source code line by line. If we drop all the memory optimization and these things happening like CPU reordering. But we can assume that lines are executed one by one. So previous line influences the next line. That's the first thing we assume. But when two machines, they work together, we say that event A influenced event B when there was a communication between machines. So if machine A called machine B, we can safely say that whatever happened after machine B received the request was after sending the communication from machine A. So this is pretty intuitive. When we are going on one machine, we just go in order. When we are going in multiple machines, then we cannot tell anything until we just communicate between these machines. And this is the algorithm, like the specification of it. But instead of going through the textual representation, let's see some example graphical one. So what we are going to do is we will have three machines here. So we will have machine 1, 2, and 3. And all these machines, they maintain separate independent clocks. Clocks here, we think of like an integer value, not necessarily the timestamp. So we can see that first machine is basically running with, let's say, 6 seconds resolution. So the clock increases by 6 seconds, yes? Second machine increases by 8 seconds. Last machine increases by 10 seconds. If we blindly follow timestamps, not the Lamport relationship, everything works fine for communication for the message A, because it was sent here at time 6 and received at time 16, yeah? This works well. This message also sent at 24, received at 40. Problems start to appear when we go from last machine, which sent a message at time 60, to the second machine, which received the message at time 56. So obviously, now we travel back in time, and this is not something which should work anymore. The same goes here, 64, we receive it in 54. So what happens if we introduce the Lamport timestamps? So we keep the same clocks again, only this time, these two messages are still correct because nothing broke here. But when we get these messages which potentially may introduce problems, what we do is we get the values of clocks from two machines. So here we would get value which was previously 56. And here we get value send time, which is 60. And these two machines, when they communicate, they send their clocks. So machine 3 sends its clock to second machine. Now second machine gets its own clock, which is showing 56, takes the clock of the third machine, which is showing 60, then it calculates the maximum of two values and increments it by 1. So that's the algorithm. So now machine third sent 60, and second machine is now updating its own clock and getting the maximum of value, incrementing it. So we can see that the next timestamp on this machine, because this machine was going like in with the 8 seconds resolution, is also 8 seconds apart from 61 to 69. The same thing is actually happening here, yes? So we are sending at 69, receiving at, previously it was 54. Now we get maximum of these two values, we increment it, we have value 70 here, okay? That's the idea of Lamport timestamps. And now, what happens with this influential, with this that event A influenced event B? So when it comes to one machine, we can say that each event influences the next one. So we can clearly see we are executing in order. They influence each other. But when it comes to these events, for instance, event 12 and 18, we cannot tell anything about these events for events 0 and 8 as long as we don't communicate. But once we do communicate, once we do have this communication here, we can say that all these events influenced all these events here. because there was a communication. So we know they get in sync at some point, and we can compare these events. Pretty simple idea, but once we introduce it, what we get is a very strong statement. Then once we know that event A happened before B and influenced B, so A influenced B, we know that clock A is less than clock B. So when we know there was some communication between machines, then we can just compare their clocks and figure out which events were happened before. Also, unfortunately, we cannot tell that about all the events. So if we go back to the example here, we cannot, for instance, tell whether event 36 on machine first happened before event 48, event 40 here. That we don't know because there were some other events between communication which happened only here. So we don't know that these events influenced each other. We probably even see that they did not. So we cannot tell which of them actually happened earlier. So that we cannot tell. But once they do communicate, we can just compare the clocks. So how do we implement this in distributed system in real life implementation? So we'll go through some very simple .NET implementation, but the idea should be generally you can transfer it to any language or framework of your choice once you just understand how it's supposed to work. So what we are going to do is we need to carry on two pieces of information. First piece is the correlation ID. So user comes to our system. We need to generate some unique identifier showing, hey, this is the workflow of the user. This is the transaction we start. So it's generated only once. It's unique. And it's also propagated across the system. Then logical time is maintained just as we've seen on the previous slide. So each node is having its own time. And when we do communicate, we need to pass the time, and we need to update the time and carry it on. So what we start with is we introduce some interface called iCorrelator, which basically gives us the access to those two pieces of information. Yes, to correlation ID and to logical time, to this Lamport timestamp. It also has a method to update logical time, which we use when we do communicate. And we can also introduce something like human-readable activity telling us what is actually happening. This will be helpful for our logging information. So we start with this correlator. And what we are doing here is we basically need to implement this Lamport timestamp right now. So whenever we do get the logical time, we just increment it by 1 because, hey, some event influenced other event, so we just increment it. This is when we are just getting the time within one machine, okay? And we use interlocked increment just to avoid unnecessarily locking, some monitors, all these things. But when we do communicate, what we are trying to do right now is we get this new time from some other system. And what we do is we just calculate the final time, which is now the maximum of these two times. And again, we do the interlocked compare exchange just to store the new value of the time, yes? So this is how we store these things. And this is the basic implementation. You can see that this class is still abstract because we need to fill in the second piece of information, which is correlation ID. But this implementation we want to use across all the nodes, all the machines in our distributed system. So what do we do next is we would like to have some logging infrastructure. So you do have iLogger interface with logging level, et cetera, and message. You do have some correlator here. And you just implement it in some way. So whenever you do log your message, you basically have the following segments. And I'm not saying these segments are sufficient or these pieces of information are all you need to debug your application, but they generally are a good start. So we do have some human-readable timestamp, like, hey, it was 2 p.m. London time. Application name, so you know where this is coming from. You do have some instance ID of your machine. Thread, either managed thread or Windows thread ID, whatever else. Correlation ID, obviously, because we need to know for which workflow this message was logged. Level for info error or whatever. Activity, so it's easier to read. And the logical time, so the Lamport timestamp. Logger ID, if you have multiple loggers in your framework, can also be useful. And obviously, at the very end, we just need to also log the message for the system. Yeah? So we do have, again, some abstract class giving us this very nice log method, which does the trick. And from now on, we just need to fill in all the missing parts. So imagine that we consider this simple example. So user comes to our distributed system. What we need to do initially is we need to generate this correlation ID and initialize logical time on the machine we are hitting with. This can be your load balancer, web server, whatever else, yes? So you just create correlation ID as GUID, new GUID, or whatever else, whatever you'd like. And you just store it in your memory-based correlator here. So you can see that it inherits from the correlator. So now correlator, the base class, provides the implementation of this Lamport timestamp. Here we introduce correlation ID. So this is when we start the workflow. Now, because we are in distributed system, we need to start communicating with some other nodes, databases, like file storage, whatever else. What we need to do right now, we need to pass all the information to the node we are communicating with. So we can, for instance, implement like our own REST client and pass these things using HTTP headers. Yes, so we add two more headers and correlation ID, correlation counter, so like logical timestamp, and we just extract them and pass them later on. Okay? So this is when we are calling some remote node within our system. What we do next is we get HTTP request. We just need to parse these things. So depending on the framework of your choice, you may have some like action filters or action handlers or whatever else, like base constructor of your activities. All we need to do is we just need to get the request from HTTP context, so to get correlation counter, and also get the correlation ID. Yeah? So we just get the request, we parse this data, and we initialize our request headers correlator. So this thing also inherits from correlator, is using exactly the same implementation, only the way we initialize these things is slightly different. What we do next is we need to reply back to the service, which called us. So what we need to do is, once again, we need to pass the new time because we finished the communication. So what we do now is we just get the same REST client which we had before, but now when the action is executed, like when we finish getting the, oh, sorry, that was one step ahead. Let's go back. We need to return the headers, so we need to once again wire them up in returning the response of our server. So this is action filter or an action executed or whatever else you do have in your framework. So the same way we previously were parsing headers which were given to us, now we are just adding them as a response, yes? So we add these two headers that, hey, that was correlation ID. Probably we don't need to return the correlation ID, but it's good to have it in case we are like examining the network traffic, and also we do have the time. And on the other side right now, we need to update the headers when the request we send comes back with the answer. So we get to the REST client again, and previously we were adding headers here. Now we just get the response, so we parse the headers and extract this data. Okay? So this is how we need to do it, or how one of the possible implementations for these things. And there are a few important remarks when we are implementing it in this way. So generally, we would like to make our life easier. We probably would like to wire this up through some dependency injection, etc. So it's always injected into all the places we have. Important thing here is I only covered the HTTP REST communication. If you are using some N-service bus, MSMQ, or whatever queues are there, file storage, etc., you always need to somehow wire up this metadata, yes, this information. So whether you add them as like metadata to the message pushed onto the service bus or the file name, whatever else, you just need to propagate it somehow. Now, you need to log this something. So this iLogger, which I presented to you, you probably would like to use it with some log4net or nlog or whatever library of your choice. Whether you put it on top of the library or below the library is like a matter of taste. And finally, what happens now? We started with this question, hey, user comes to our system, something went wrong. Now the user needs to figure out or asks us, hey, go and figure out what happened. So what we need to do right now is we just show the user, hey, this is your ID. When you reach out to us, please give us this string. So this is the correlation ID. User comes to our support and tells us, hey, you wanted me to give you this string back. We just grab this string, we go to our logstash, Kibana, OMS, whatever else we have, and then we just filter out logs based on correlation ID, order them based on the Lamport timestamp, and as long as we do know what's going on in the system, because we need to keep in mind that which events influence which others, we can just order them and go through them one by one. So this is the idea, how to sort these things and how to make the logs much clearer. OK, but that's just the beginning. What we were considering until now is there is one user coming to our system, and he starts a workflow. But if there was another user and she was starting another workflow, we assumed we don't want to compare these things. Now, the question is, can we somehow extend this system to be able to compare all the events in it so we can safely say or easily say that, hey, this event happened before that event, and that event can be any event in our system. Because as long as we do not want to do this, we can go with simple Lamport implementation, and it works for like one constrained workflow. But once we want to compare everything with everything, it's getting harder. So we won't solve this problem in its entirety, because this is actually a lot of computer science research. What I'm going to show you is how these problems are tackled and what components we need to have to solve all of them. So first thing we would like to introduce is a concept of vector clocks. So previously we had a logical clock. Each machine had one value, its own independent clock, right? What we are doing right now is each machine is going to have a vector of clocks representing the state of the clocks of every other nodes. So what we do now, instead of seeing the text representation, let's see it here, we just introduce the clocks once like on the go. So each machine starts with just one clock, its own clock. But then once they communicate, they pass the clocks, and then once again implement this logic for getting maximum of the clocks and incrementing them, yes? So you can see that C here communicates with the machine B, and it passes its own clock with value 1. So then machine B gets their values, and from now on, it stores 2 clocks for B and C. Then, when it communicates with A, it passes these clocks, etc., etc. So we just communicate, we exchange all the clock values. So in theory, we should know what's the time on every other machine. Now, what this gives us is, previously our clock was just one integer. Now our vector clock is basically a vector, so we have multiple values of there. And then we introduce this comparison relation again. So this time we say that vector clock of A is less than vector clock of B. If for each component's vector clock of like this component, matching components, is not greater, and there is at least one component which is strictly less than the matching component of the other vector. Once we do have this relation, we can say that if we know that vector clock of A is less than vector clock of B, we know that A happened before B. This is something we didn't have before. Previously, we did know that if A influenced B, then their clocks was strictly less than the other. But now we can just compare the clocks, and as long as they are in this relation, then we can tell which event happened before the other one, okay? Obviously, by definition of this relation, you can say that not all the events will be comparable, yes? Because it may happen that one component is strictly greater, the other component is strictly lower, yes? So it's not sufficient to compare all the events, but once we have this relation, it's a step forward how to do it. And there are some other generalizations of these clocks, obviously, so they are slightly more efficient when it comes to like how many clocks we store, so make this vector smaller, etc. But generally, they are all based on the same idea. What we do next is we need to introduce or understand what we are exactly dealing with. So we introduce a concept of Byzantine generals, and there is a name of, or this means an effect when our machines, they start behaving weirdly. So a short story. Imagine that all these generals, so there is one general, multiple lieutenants, there is an army which basically wants to attack some city, yes? So general makes a decision, hey, we are going to attack now. And general is sending this information to all the lieutenants. But then one of the lieutenants is malicious. He wants us to lose. So he starts lying to others and says, hey, the general told us to retreat. So we can clearly see that once we have a lieutenant like this malicious lieutenant, things may go pretty bad. Because if general cannot reach out some other lieutenant, then the malicious lieutenant may pass incorrect information to that one. So we may get out of sync and get like split brain in this situation. And now how does this apply to computer science? And here we can imagine that each of people here is basically a separate machine. And the attack or retreat order is basically a network communication. Now, if a machine has this so-called Byzantine fault, it means that it goes and behaves completely unpredictably. We would like it so when the machine fails, we would like it to probably remain quiet or just die and never come back. However, in reality, it's not the case, because in reality, in distributed systems, all the components can fail, but the failure may be of different types. The failure may be that the node just dies and never returns. It may be that it starts violating the protocol, sending the messages when it's not supposed to be sending them. It may be that it's repeating the messages, or it may be sending out broken messages. Broken messages here is basically saying this retreat instead of attack. Okay? So once we get to this situation, when we cannot trust any of our components, how do we actually figure out what's the order of things in our or in our distributed system? And this is not a question of if something goes wrong. This is a question of when these things happen, because in distributed systems, everything is going to fail sooner or later. So what we are going to do right now, before we get to ordering events, is we would like to figure out how do we get one value, assuming it was replicated across multiple nodes. So there is some info stored in the database. We would like to read this info, yes? And what is going on? We say that system is k-fault tolerant when it can survive failure of k nodes, at most k nodes. So now the question is, how many nodes do we need to be able to extract this piece of information when k systems can go down? The answer is, in that super simple situation when we don't have Byzantine failures, it's k plus 1. Why? We just ask every single of k plus 1 systems, and one of them must be working properly because only k are allowed to die, yes? Or we assume only k will die. So in that case, it works. But if we do have Byzantine failures, then it's not sufficient to get k plus 1 answers or ask k plus 1 systems, because the nodes may lie to us. They may give us incorrect answers. Hey, what's the value of this variable? And it's basically lying. What we need to do is we need to do the majority voting. So we ask 2k plus 1 systems. K of them are lying. We get answers from other k plus 1, which is correct. And because of majority voting, we can safely deduce that, hey, this was the correct value. So this is when it comes to reading. But how do we modify this value? Imagine now 2 users come to your system. User A is in London, user B is in Tokyo. They want to buy the last piece of something, and you need to decide which of them was actually the first one to ask for that item. So now we need to solve the so-called consensus problem. So we need to agree on some decision. And to agree on that, we would like to have nice protocol which basically fulfills these properties, which are like mathematical ideas. But basically, this should be pretty robust and pretty stable, yes? So when the machines finally agree on something, they agree on the same value, and this value was proposed by at least one machine, yes? That's the idea. We obviously specify that there is a termination, so there is a finite number of steps, so it's not going like forever, and the integrity and all the other things. So this is the problem we are now trying to solve. So we were capable of reading something, now we are modifying something. So if we assume that we do have k-fault tolerant system, so k components die, we need actually 3k plus 1 nodes in our system now to solve this problem. Why is that? That's because we need to not only agree on something, but we also need to convince others how we are going to do it. The problem is we implicitly assumed something about the communication under the hood. So we assume that the communication basically does not disappear. It may be bounded or bounded. There are some timeouts. And if we focus on mathematical analysis of this, we can prove that, for instance, the first rectangle here is if we have synchronous, unordered communication, unicast and bounded delay, consensus is not possible when only one machine out of this 3k plus 1 die. If one machine dies, we are not able to achieve the consensus. And it's proven that only in these situations here marked in green, yes, it's possible to get the consensus to agree on something. And there are generally a lot of different algorithms. There are pretty big research and white papers telling us how to do it efficiently, how to minimize the number of messages, why it's not possible, and it's proven it's not possible, so it's not something we suspect. So generally, there is a big math behind all these things. And just to give you an idea how this thing works, there are multiple protocols. One of them, of the protocols for achieving consensus, is called Raft. And in this protocol, basically, we do have a big state machine for each of the nodes in our system. And each node can be in one of the multiple states. And now, it seems pretty easy, but proving that this state diagram and these transitions are sufficient to achieve the consensus, it's actually quite a lot of maths behind it. So generally, each node can be in like one of the multiple states. And general assumption is there is like a leader at some point, and the leader is pinging all the others. When the leader dies, the followers, so the nodes which are receiving this ping message, they notice that the leader died because the ping did not return or something like this. So now followers need to decide who is the new leader. So each follower says, hey, I'm the new leader. Do you all agree? Other nodes may say, yeah, I agree, or no, I do not disagree. They pass some messages, integers, et cetera, and finally they deduce who the leader is. So it seems simple. There are multiple issues with this approach, because first, if leader is unreachable pretty often, so if the leader changes, it may be that we are actually capable of determining who the leader is, but it takes so much time that our performance basically decreases too much. It also may be that the leader is decided just for one decision, and then the leader election starts to happen again. So we basically spend a lot of time to decide, OK, who the leader is. Then the leader decides on one thing, and then it dies out or whatever else, and we need to decide again. So there are multiple issues with these approaches. But once we do have this consensus, we can implement, that is, again, mathematical proofs, that we can implement these operations here in distributed system. So for instance, we can do the total ordered broadcast, which is basically a communication that I send a message to all the nodes in my system, and I have a guarantee that this message happened before other messages or after other messages, and that all the working nodes, which are still working correctly, they do receive this message properly, and they acknowledge it, and they commit it, etc. We can also implement distributed compare and set. We can also implement distributed increment and get. So we can finally agree on the order of events. And once we can do that, like solving the issue we had with logs is now super simple, because in theory, we can just communicate each other and say, hey, I'm logging this now. OK, they decide who the leader is. They elect. They store it. Obviously, we are not doing it this way because it kills the performance. But we can agree on things like, hey, two users are trying to buy this one item. Who wins this idea? Obviously, now there are other questions like whether we want this consistency. Maybe we would like to have eventual consistency, whether we don't need this distributed transactions at all. But this is like a story on its own. And just to give you an idea how these things are hard, there is a project called Jepsen. Jepsen is supposed to evaluate distributed systems and show that they are working or they are not working correctly. So the owners of, for instance, MongoDB and other distributed databases, they reach out to Jepsen people and they try to evaluate whether this works correctly. So once you get to your database tutorial or documentation and it tells you that, hey, we have this strong consistency guarantees of all the things, it's easy, like if you do have proven it by Jepsen, then you probably can safely assume it's working as expected. And Jepsen already showed that multiple databases were losing data pretty often, were not honoring the consistency they were guaranteeing, etc. So take a look at this. Google some YouTube videos about Jepsen, how they were proving things. Summary. Wall clock, as we've seen, is pretty tricky, and it's not usable in distributed systems. Lamport timestamp is a way to do it if we do have sufficiently simple situation. If we do have harder situations, then we probably need to use some well-built distributed systems, which are also evaluated correctly and basically guaranteed to work properly. And all these things, you always need to assume that, hey, these things will go wrong. Your machines will die, your machines will fail, and you do have Byzantine failures. So those things will not work correctly. OK, having said that, it's time for QA. Any questions? This is the QR code pointing to the slide deck, by the way. So if you would like to download it, that's the way to go. Questions here? OK. I don't see any questions. Feel free to reach out to me offline or after this talk during the conference. Before we'll just wait a few seconds for people to scan this QR code, and then we'll just wrap up with some resources, references. So if you would like to read more about distributed systems, you are now interested in these timestamps, vector clocks, all these things around, there are some books I think I can recommend for you. So you can start with Tannenbaum Distributed Systems Principles and Paradigms. That's pretty nice introduction. And also Designing Data-Intensive Application is a pretty good one telling you how to implement these things working in a distributed fashion and giving you a very good performance. Yeah, there are some other books as well. Feel free to take a look at them. Also, if you would like to read things on the internet, some links for you to read about Lamport timestamps or all the funny stories about like Sweden, February 30, and all these things. So falsehoods programmers believe about time. Logging in distributed system implementation. This is basically my blog post series with this implementation. So you can get the slide deck from there or get the code which is supposed to be working correctly. And having said all of that, I'd like to thank you for attending this talk. My name is Adam Furmanek, and I hope you enjoyed it. Thank you.